Notes for section 8.0, I call it, because I actually stole this from chapter 1 when they were talking about polygons in chapter 1 as kind of an introduction, but all of chapter 8 talks about polygons. So I kind of switched it over and put it in chapter 8 as first. Polygons, what you need to know, some definitions, and I'm going to go through this too fast for you, so you're going to have to pause the video and write it down. It's formed by 3 or more segments, polygons are. No two sides with a common endpoint are collinear, and I'll go back and explain that. And we also have each side intersects exactly two other sides, one at each endpoint, vertex. It's a very complicated way of talking about polygons, but those are the true definitions of them. Formed by 3 or more segments. So your polygon has to be segments. This is no fun if it doesn't actually write. Let's try that again and see if it's a little quicker. 3 or more segments is a polygon. Of course, you don't have to have the little points on it. So triangle would be your first one, and then a quadrilateral after that. So technically, if these were all lines that went on continuously, that's not truly what a polygon looks like. No two sides with a common endpoint are collinear. You could not get away with calling this a 4-sided figure. It's only 3-sided. It's a triangle. It says no two sides with a common endpoint. Here's your common endpoint. Those two sides and those 3 points cannot be collinear. It's going to have to be non-collinear to make it another side. And then the third one, each side intersects exactly 2 other sides, one at each endpoint. Each side intersects exactly 2 other sides. So we're not going to have any polygons that look like this and say, all right, this side intersects 1, 2, 3 different sides. It can only intersect 2 different sides, one at each endpoint. And I'll go back up to this. These have to also be segments, which means a circle is not a polygon because it can't be circles. It can't be something that has any kind of curved surface. They have to be segments, not lines or arcs or curves. So it's pretty much what you know about a polygon, but more specific in the definition. Next up, when you name a polygon, this is a 5-sided figure. When you name a polygon, you start with one vertex. It doesn't matter which one. In this case, you started with T. But it does have to go in order after that. T, P, Q, R, S. So you could name this T, P, Q, R, S. And then it would go back to T. Or you could name it T, S, R, Q, P, T. And do it exactly backwards. Or you could start over here at Q and name it Q, R, S, T, P, Q. It doesn't matter where you start and end as long as you go in order. If somebody else named this polygon T, P, R, Q, S, T, P, R, Q, S, that is not correct. It has to be named in order. Another thing I'll point out, it doesn't have a symbol in front of it. Triangles have symbols in front of it so that we know it's a triangle. We know this is a 5-sided figure because it has 1, 2, 3, 4, 5 vertices. We know quadrilaterals have 4 sides. The reason why we need a triangle symbol is so we know it's not a plane, because planes and triangles both need 3 points. Okay, both of these are polygons. They fit all 3 definitions, and they have 4 sides, 4 sides. They look a little completely different, but yes, they are polygons. And these are not polygons. This one fails the number 1 rule. It's not made of segments. This one fails the number 3 rule. It doesn't have, how did they say it? 2 endpoints. Each side intersects exactly 2 other sides, one at each endpoint. It did not intersect 2 other sides, one at each endpoint. So it failed the 3rd rule or definition. Same as this one. It did not pass the 3rd definition of intersecting only 2 sides. And technically, you could say it also fails the second definition. No two sides with the same endpoint are collinear. So you can't count this as a side and this as a side. So know the difference between what is a polygon, those two both are. What's not a polygon, those three are not. All right, next up we're going to name our polygons. What is a 3-sided, a 4-sided, a 5-sided, 6-sided? We'll go all the way to 100. Kind of, all the way to 100. Can you see me? It's like really dark in here. If you know them already, try it. See if you can write them down without seeing them here. Try all of them, and if you get stuck, come back, turn on the notes, and see. Number 3 is a triangle. Number 4, have to call it a quadrilateral. You can't call it a square, a rectangle, a rhombus. All of those are quadrilaterals. They're just more specific types of quadrilaterals, and we will get into those a lot more in depth. 5, pentagons. 6, hexagon. Slow down and check the spelling on these. You have to be able to spell them correctly. 7, I've seen and heard both, depending on where you look, can be called a heptagon, also can be called a septagon. 8, octagon. Makes sense. Octopus has 8 tentacles. Octagon has 8 sides. October is the 10th month. September is the 9th month. I know. That part totally doesn't make sense, but actually it does. The original calendar, somebody maybe Google this and check it. I'm pretty sure the original calendar back in the day did not have a June and July. So if there's no June and July, then September was the 7th month, October was the 8th month, which would explain that. We also have 9, 10, 11, 12, 15, 100, and N, and 22-sided figures. What are all their names? A 9-sided figure, nonagon, with an A. Non-a-gon. So are the other spellings. Pent-a-gon. Hexagon. But it's penta means 5. Gon is the polygon. Hexa means 6. Gon is the polygon. Now I'm giving you an English lesson. Hepta or septa is 7. Then you attach the gon. Octa is 8. Then you attach the gon, which is important. You're going to need to know how to spell this in a second. Nana is 9, and then tack on the gon. Deca is 10. Decathlon, decade. Deca is 10, tack on the gon. 11 does not have a name. Somebody skipped 11, poor 11. But the way that you write the name of a figure that does not have, the name of a figure that does not have its own name is 11 with a hyphen gon. It's called an 11 gon. Just like this called a deca gon, a nana gon. It's not a dec-agon, non-agon, 11 agon. You don't put an A in there and call it an 11agon. That's not correct. Gon is the suffix that you put on the end. 11gon. Just ask your English teachers. Number 12, dodecagon. Do for 2, deca for 10. 2 plus 10 is 12. Dodeca, suffix gon. 15, knowing what you know about the dodecagon, see if you can guess what a 15-sided figure is. I'll give you a hint, it's 5 plus 10. Pentadecagon. So pentadeca, and then it's a gon. And 100, if you know anything about counting or pennies or 100 years, centagon. Centagon. So what is an n-sided figure called? You don't know how many sides it has. It is called an n-gon. Not an n-agon. It's an n-gon. A 22-sided figure or anything else that you don't know, 22 with a hyphen, gon. Yes, you have to memorize these. You've got to know what they are. I don't know why it's so dark. Let me try turning on another light. See if that helps. Maybe. But yeah, you got to memorize them. And you got to pretty much know how to spell them. Centa, pentadeca, dodeca, 1 through 15 are probably the most common. More vocabulary. Convex. If you have a convex polygon, no line that contains a side contains an interior point. Again, way too complicated. Write it down because it's a description and it's vocabulary. But what does that really mean? It means if you have any polygon and you draw a line through that side, it will never go inside the polygon. So basically you can outline it. It would never go through the polygon. If it does go through the polygon, then it's called concave. I always like to think of it as it caves in. If it caves in, it's concave. If it doesn't, it's convex. So if you look at these, and if I trace my sides and make a line out of it, this is definitely convex because no lines that contain a side actually go inside. And I could try that here, but once I get started, those all work, and now I do this one, I just went inside the polygon. So this one is concave. This one is convex. Did it cave in anywhere? All right, more vocab. There always is when you start out a chapter. Equilateral versus equiangular versus regular. Check the spelling again. Equilateral. Lateral means sides. Side to side. If you move laterally, you move side to side. Lateral sides. Equal sides. That's this one. All sides are marked equal. Equal. Notice there's no L in that. It's not called equiangular. Angular means all the angles are congruent, but not the sides. If it's called a regular polygon has both. All the sides are congruent and all the angles are congruent. Has to have both. So that one is considered a regular polygon. More vocab. Diagonal. Again, pause it and slow it down if you have to. A segment that joins two non-consecutive vertices. We learned that word in chapter 1. Non-consecutive vertices. So if I pick this vertex, I can't do the vertex next to it. I can't do the vertex next to it here. I have to go to the vertex down here. So this quadrilateral has two diagonals. This quadrilateral has two diagonals. This hexagon has 1, 2, 3 diagonals. Keep going. 4, 5, 6 diagonals. And you might say, oh, if it's got 3 at each one, 3 times 6 is 18 diagonals. No, that's not true. Because then you're going to come here. You don't get to count this diagonal back to there again. This has 2 more. This has 1 more. And now we have them all. So if you counted how many diagonals, we'd have 1, 2, 3, 4, 5, 6, 7, 8, 9 diagonals in a hexagon. In a pentagon, 1, 2, 3, 4, 5 diagonals in a pentagon. In a triangle, there are no diagonals in a triangle. So all quadrilaterals have 2, all hexagons have 9, all pentagons have 5, triangles don't have any. Next, it's going to ask you specifically to name the diagonals on the pentagon. And when we name diagonals, we name them as segments, as they are. Name the diagonals on the pentagon. We have segment AX. We have segment AZ. You could call them XA and ZA, of course, segments. We have segment HP. We have segment HX, or again, segment PH or XH. And we finish with segment ZP. You don't keep going around and calling them again. They are the same forward as they are backwards. There's your 5 diagonals. Name the diagonals that have Z as a vertex. What diagonals have Z as a vertex? You can tell by the diagram, AZ and PZ, or you could tell by your list. If it says specifically that has to have Z as a vertex, then those are the 2 that works. Again, order doesn't matter. All right, let's finish these up with a word problem. A table is shaped like a regular hexagon. So here's where your vocab comes into play. They're not going to explain it every time. Regular hexagon means that you have all sides and all angles are congruent. The expressions shown represent side lengths of a hexagonal table. Okay, so he's sitting at a hexagonal table. We know that it's regular, so all sides are congruent. We probably don't even care about the angles right now. They just want to know find the length of a side. We have nothing to go off of because we don't know the perimeter of the whole thing, or we don't know the length of any one side. But we do know that in a regular hexagon, all sides are congruent. If all sides are congruent, that means their measures are equal. Do the math from here. I'm going to minus my 3x over this way, add my 2 over this way, and get 8 equals x. Don't stop there. That's algebra. Geometry. Find the length of a side. Plug it in. 4 times 8 is 32. 32 minus 2 is 30 inches. Double check. 3 times 8 is 24. 24 plus 6 is 30 inches. That's it. That's your little lesson on polygons and all the vocab that goes with it.